Hello, and welcome to the next video in my series on finite mathematics. Now, a few things before we get going. Number one, if you're watching this video because you're struggling in a class, I want you to stay positive and keep your head up. If you're watching this video, it means you've come pretty far in your schooling up to this point, and this rough patch is just temporary. So with the right amount of hard work, practice, and perseverance, you can get through it. I have faith in you, and so should you. Number two, please feel free to follow me here on YouTube and or on Twitter. That way when I upload a new video, you know about it. And finally, just remember that these videos are geared towards individuals who are relatively new to finite mathematics. So the examples and explanations I'll be going over are very deliberate. I'll be going very slowly, and I will explain every single thing we do so you know exactly what's going on and why it's going on. So all that being said, let's go ahead and get started. Now this video is the next in our series on Markov chains. So we've talked about Markov chains at the most basic level, what they are. Then we've talked about one-step Markov chains, so one step into the future. Last video we talked about two steps or two steps into the future. And at the end of that video, we started to talk about developing a general model for Markov chains that run far into the future, say 5, 10, 15, 20 steps into the future. Now, of course, making a probability tree that long would be immense. It would take up the size of a wall to do all that. So therefore, we use matrices to figure that out. So in this video, we're going to go ahead and continue that discussion of long-run Markov chains or long-run transitions. So we are going to build on the problem we used in the last video. Now, I'm not going to re-explain Markov chains, so I assume you've either watched my previous videos, you've watched other videos, or you've at least gained something from being in class or from your textbook or your notes. So I'm not going to re-explain all this in terms of basic Markov chains. I'll kind of assume you know what I'm talking about in that respect. So let's go ahead and dive right into the video. So just to recap, we have an insurance company that, of course, signs up new customers for its policies. And when they do so, the customer will either be low risk or high risk, depending on whether or not they had a ticket in the past 12 months. So they walk through the door, they check the driving record. If they have had a ticket in the past 12 months, they get put in high risk. If there's no ticket in the past 12 months, they go low risk. Now, based on government data, we sort of estimate that any random driver out on the road has a 10% chance of having had a ticket in the past 12 months. So you're at a stoplight, you look over next to you, there's someone sitting there, and there's a 10% chance that person next to you has had a speeding ticket in the past 12 months. Just a random driver out in the general population. Now, based on the company data, internal to the company, so its own policyholders, if a driver is high risk now, there's a 60% chance they will be high risk when they renew their policy a year from now. And therefore, that means there's a 40% chance they will not be. They'll be low risk. So notice those add up to 100%. Now, someone that's low risk right now has a 15% chance of moving to high risk when their policy renews, or an 85% chance of remaining low risk. And again, those probabilities add up to 100. So for this video, the question is, if all the new policyholders that walk in off the street to sign up for insurance are representative of our general driving population, that's the 10% and 90%, what will be the company's high risk, low risk distribution many years from now? So in the previous videos, we've done 1 year from now, we've done 2 years from now, and now we're going to talk about many years from now, 5, 10, 15, 20 years. So just a few reminders. We have our transition matrix, and this is just the information we talked about a minute ago put into matrix form. So a driver that's currently in our insurance company If they're high risk, there's a 60% chance they'll be high risk when they renew. So that's 0.6. High to low is 0.4. Notice those add up to 1. And then below that, we have low risk to high risk. So there's a 15% chance of moving from low risk to high risk when the policy renews. And 0.85 for low risk to low risk. And again, this is just the probability of going to any of the two states when the policy renews next time, depending on the driving habits of our policyholder. Now we also have what's called the initial state vector, which are just the probabilities we assign to customers when they walk in off the street to come into our insurance company. So they walk in the door, we go over their driving history. If they've had a ticket, they go into high risk. Now based on the random population, we estimate that to be 10% or 0.1. So that means, of course, there's a 90% chance or 0.9 that they have not had a ticket in the 12 months before when they walked into our office. So we figured this out as far as one step into the future. We multiplied our initial state vector, which is 0.1 and 0.9, times our transition matrix, which is there next to it. And then we do that, we come up with a probability in the high category of 0.195 and in the low category 0.805. So what this means is that if a new customer renews with us after 1 year, the probability that he or she is high risk or low risk is 0.195 and 0.805 respectively. And that's pretty cool. So if we're sitting at the desk and someone walks in, we know based on probabilities out in the general population and the probabilities internal to our company, which category this driver is likely to be in next year when they renew. So that's our one-step probability. Now, after that, we did a two-step probability. Now, up to here is our one-step. So this is exactly what we just did in the previous slide. They walk into our office, they get put in a category. Then 1 year later, they renew, they get put in a category again. And that takes us up to this picture right here. Now, if we go 1 year into the future from there, they can go into each category as well. So it looks like this. So this is 2 years into the future. And it's a simple probability tree with each outcome there on the end. Now you can see, once we get up to, say 5 years from now, think of how big that probability tree would be. It would be almost impossible to write unless you had a piece of paper, the size of a room's wall. So that's why we use matrices. Now we talked about the probability for each outcome by multiplying through each path. So if you look there at the top, the probability that a customer comes in, they're high risk. 1 year from now, they're high risk again because they got a ticket. 1 year after that, they're high risk because they got a ticket again in that 12 months. Is 0.1 times 0.6 times 0.6. And that equals 0.036 or 3.6%. So to find the probability of each path, we just multiply them through, and then at the end, we have it for each outcome. Now, of course, when we add those probabilities up, they're on the right-hand side, they equal 1, and that's because they have to equal 1. That's just sort of a fundamental, basic, the nature of these things. So this was our one-step probability, and this was in a slide or two ago. We took our initial state vector, multiplied it by our transition matrix, and then we got our one-step probabilities of 0.195 for high risk, 0.805 for low risk. That's 1 year from now. So if we go one more step into the future, what can we do? Well, we can take our answer from the one-step probability, multiply it by our transition matrix again, and then we have a two-step probability. So 0.258 of being in the high-risk category, and a 0.742 probability of being in the low risk. So all we did, we took our solution from the one step, we multiplied it or sort of ran it through the transition one more time, and now we have our two-step probability. So if a new customer renews 2 years from now or after 2 years, the probability that he or she is high risk or low risk is 0.258 and 0.752 respectively. Same process, but because of the probabilities internal to our company, we have to figure out the probability of high risk and low risk once they are a part of our insurance company. So you can see a pattern begin to develop here. We're taking the answer from a one-step, multiplying it by the transition matrix again, and then we get our two-step. So this is our short two-step version. And this is what we just did compressed into one operation. We have our initial state vector on the left-hand side. We have our transition matrix right next to it. And then we have an exponent of the transition matrix, which is the number of steps from now we are interested in. And in this case, it's 2. So if we go into our graphing calculator, which I showed you how to do in the last video, and we do this in our calculator, we end up with 0.23775 for high risk and 0.76225 for low risk. So there's another, you can see the way of doing that. You can just put it into your calculator and then do it the exact same way, and you'll get the exact same answer. So now let's talk about the long run general form. And you can see there's a pattern here. It should be becoming fairly obvious to you how this is going to work. So what we have our initial state vector. We multiply that by our transition matrix. And then we have an exponent, which we call m in this case, which is the number of steps from now. So again, this is just a general form. And our answer will be the probability of being in each state m years from now. So if we're interested in the probabilities 5 years from now, our exponent above the transition matrix would be 5. And that would give us our 5 years from now probability. So another way to put this in sort of a general form, how you might see it in a highlighted block in a textbook. The probability distribution for each state after m steps. So we have V, which is our initial state vector in this case. P is our transition matrix, times P, times P, times P, etc. And remember, when we times something by itself, we can do it with exponents. So if you look at V times P, that's what we just did in the previous slide. But we're interested in however many times we want to go. So we can generalize that into this form. V, which is our initial state vector, times P, which is our transition matrix, raised to the m power, depending on how many steps into the future we're interested in. So for example, we can have our initial state vector, 1.1 and 0.9, our transition matrix, which is always the same, and our exponent, which is m, and that can be anything we want it to be depending on how far into the future we want to look into. So let's look at this. If we take our initial state vector, multiply it by our transition matrix squared, in that case m is 2, we end up with the probabilities we had before, 0.23775 and 0.76225, so that's high and low. Now let's change the value for m. Now this is 5 years into the future. So now our probabilities are 0.26953 and 0.73046. And again, that's high-low. It always goes in the order high-low. Now let's do 10 years into the future. Now our probabilities are 0.27267 and 0.72733. How about 20 years into the future? Now we have 0.27272 and 0.72727. Okay, how about 25 years? 0.27272 and 0.72727. Well, that looks odd. What's going on here? Well, once we get to 20 years and then 25 years, the probabilities appear to remain constant or steady after those numerous steps. And that's actually very important. That will be the center topic of our next video. But you can see, as we increase m to higher and higher numbers, in the case of this problem, around 20 or 25 years into the future, the probabilities become steady. They stop changing. Okay, we could increase that m, that exponent, to something crazy like 50 years, and it would still be 0.27272 and 0.72727. All right, so here is the last one we did. This was 25 years, and you can see those are our probabilities. So it would appear that after 25 years, approximately 27.3% of drivers in the insurance company will be denoted high risk. And if you remember, that's much higher than the general population. So our insurance company may be one of those that caters to higher risk drivers. And of course, our premiums and things reflect that. Now, on the other hand, approximately 72.3% will be in the low risk category after 25 years. So think about this. Someone walks into our insurance office right off the street, and we can, think about into the future, 25 years into the future, the probability that that new customer is in the high risk category 25 years from now is about a little bit over 27%, or 0.27272. It's pretty cool. So we can think of this as the insurance company's very basic driver risk profile over the long run. Now, I'm not going to go into insurance here, but we know that there are other factors that tend to correlate with risky driving behavior, namely younger people, males, and things like that tend to correlate more with risky driving behavior. But our random driver off the street, we're not taking into account any of that. This is just a random person of any age, sex, whatever, that just walks in off the street. So this is a very basic risk profile for drivers. So after 20 to 25 years, the risk probabilities cease to change. They become steady. And we actually just showed that, or sort of proved it, in the previous slide. So here's what kind of happens. Eventually, when continuing to multiply our answer at each step by the transition matrix. So we get an answer, we run it through another transition, we get an answer, we run it through another transition, get an answer, run it through another transition, etc. Once we do that over and over and over again, it ceases to have any effect on the outcome. The probabilities do not change. So 25 years into the future is the same as 50 years into the future. So we can represent that like this. So as we sort of go towards infinity years into the future, whenever we multiply that by our transition matrix P there in the middle, we get our initial distribution vector back. It doesn't affect it. It's almost like multiplying it by 1. It doesn't change it. We get it back. So multiplying by P, the transition matrix, after a while, has no effect. It just returns our initial state vector again. So in real world terms, in this problem, what happens, drivers will continue to move between high risk and low risk states year to year. But over time, with the probabilities we have, the numbers going from high risk to low risk, or low risk to high risk, become the same. So you basically trade drivers between high risk and low risk over the long run, because the probabilities stable out. So therefore, the proportions in each state will remain the same. And this is a very important thing in Markov chains and other Markov processes that we'll talk more about again in more depth in the next video. All right, so that is our discussion, or the beginning of the discussion about long-run Markov chains or long-run transitions. So we went from one-step transitions in one video. Then we went to two-step transitions in a second video. And in this one, we talked about longer run transitions, many steps into the future. And what we found out is that the probabilities stabilize. Now, that doesn't always happen in Markov chains. There are exceptions to that, and we'll talk about those in another video. But most of them will stable out at some point over the long run. Now, we found out what those probabilities were in this example by just doing them in a graphing calculator multiple times. So I could just change the exponent in my calculator from 2 to 5 to 10 to 20 or whatever. However, there is a way to actually find out what the long-run stable probabilities are using a little bit of matrix operations and algebra, which is what we're going to tackle in the next video. So just a few reminders before we sign off. Number one, if you're having problems in a class, I want you to stay positive and keep your chin up. You are smart and talented, and this rough patch is just, a brief thing that you can get through. So keep working hard, keep practicing, and keep persevering. Again, please follow me on YouTube and or on Twitter for new video notifications. If you did like this video, give it a thumbs up. If you think there are things I can do better, please leave a constructive comment below, and then I will integrate that into future videos. And finally, above all else, thank you very much for watching. The best of luck, and I look forward to seeing you again next time.